is unstable. She seems to be admitted now. So here we say is assume that V is an FG module. This is the same thing I've just spoken about, the fact that this map that sends G to this matrix of the endomorphism induced by G, this map turns out to be a representation. We can prove that. So the first bit, there are two things to prove. The first is to show that this Fn with the multiplication given is an FG module. So that is straightforward. There are these 5 properties that you need to check. We saw in the definition. Already we had checked them before. So now we're just writing them down. We had checked them before. Before we defined an FG module, we checked these properties. This is a multiplication that is given. So now, because of the way this works, we have V is sent to the vector V multiplied by the image of G under this representation. The image of G is just a matrix. So you can take this matrix to be your, this is V. Our endomorphism now will take a vector V and send it to V multiplied by image of G. So if you take your matrix, if you use the standard basis, the matrix now will just be the same as, sorry, I'm making a mistake there. This matrix that we are looking for that represents the linear map, this matrix will just be the same as this matrix. If you take the standard basis, because if you take the standard basis, then the matrix, this matrix now will work. If you take a different basis, then the matrix will change. So this answers the question that there exists a basis for which the matrix of transformation is just the image of G. And that basis is the standard basis. Someone be knocked out again. I can hear the, I think it's Janet who had been knocked out again. So this one requires a bit of attention from you. You need to pay attention for it to make sense. So the next thing is to check that this map that sends every element G, of course, for a fixed basis to the matrix with respect to the given that basis, this map is a representation. So to check its representation, you just need to confirm that this is indeed a homomorphism and that these matrices are invertible. So to check its homomorphism, you need to check if you get a product of 2 elements, where is it sent? It's sent to the matrix GH, right? Matrix for this element GH. So that becomes your new matrix. But you need to check what happens. How do you get this matrix? This matrix is the one that is determined by this element. But since this one is a what? This V is an FG. Yeah. So the way this is defined, this is the same as multiplying this by phi of GH, but we know that phi of GH is supposed to be a representation already, so you can split it into phi G and phi H. Right? So, but this is the same. This is the same as the matrix of G times the matrix with respect to H. Of course, the basis is the same. So what that means is that this matrix is equal to the product of the matrix of G and the matrix that is determined by H. Because of this, you can come to this conclusion. So that makes this one a homomorphism. The only thing left to be sure it's a representation is to confirm that these matrices are invertible, because a matrix, it can only be invertible if it can only be a representation if these matrices are from the general linear group, which means they must be invertible. Is that making sense? Yes. Think that you take advantage of this being a FG homomorphism, this property will be true. In FG module, this property holds. But the other thing that we know also is that this identity element in the group can be written as a product of G, any element G and its inverse will give you what? It will be the benchmark. It determined by 1. This will be just the identity matrix because it doesn't change the vector, right? So the matrix representing this endomorphism will be the identity matrix. But we know very well that we have checked that if now you want to get the matrix that represents these two, then this ends up being the product of the two matrices, one for G and the other one for G inverse. So what does that mean? Each one of these matrices has another matrix whose product gives you the identity. So that means the matrices are invertible. So we can conclude that that map gives you a representation of G. Are we together?
Yes.
Good. So let's look at an example. We consider this dihedral group, the symmetries of a square. These are the defining relations for the symmetry of a square. So then we have this representation that we defined earlier. Remember this matrix, I think we call this one A. This we had to call this capital A and the other one B. We defined this representation earlier. So we already know that we have a representation here. So this is from the general linear group of 2 by 2 matrices. So we can pick our vector space to be the Euclidean 2 space or F2. F2 where F is either the set of the field of real numbers or the complex numbers. Any of them will work. Then V, we know this will be an FG module from what we had defined earlier, with the multiplication defined as this, where Vg is sent to V multiplied by the image of G under the representation. So we can if you want to fix So this just gives an illustration of a multiplication where you have a vector V, which is a vector 1, 0, then it's acting on A. So this this multiplication will simply be equal to the vector multiplied by the image of A under this multiplication. So under this multiplication, 1, 0 will be sent to 0, 1. Okay. Now let's pick any two elements from the Euclidean two space. Suppose they are this standard basis with the vectors 1, 0, and 0, 1. Then we can make the following assertions. To get the matrix, now we need to get the matrix for A. So this is what we are looking for, getting this matrix for the endomorphism induced by this element A with respect to this standard basis. We call it B, just to, then that becomes our subscript. So this is the matrix we are looking for. So the map that we are going to consider is every element V will be sent to VA. So this is now the linear map. The endomorphism that we will be considering, whose matrix we are looking for. So to get the matrix, you need to get the images of the basis elements, right? So V1A is sent to V2. If you can check, we have seen that if you have V1A, it's sent to 0, 1. So V1A will be sent to V2. And V2A, you can check this by doing the multiplication yourself, will be sent to minus V1. So this matrix that we are looking for, and then what happens is you now have to write this as a linear combination of the basis elements, right? So V2 can be written as 0 multiplied by V1 plus 1 multiplied by V2. And minus V1 can be written as negative 1 multiplied by V1 plus 0 multiplied by V2. So remember this matrix that we are looking for, the matrix for this representation. We had discussed this last time. How do you obtain it? You simply pick the coefficients. That will be 0, 1, then negative 1, 0. So this becomes your matrix for the linear transformation that is induced by A with respect to the given basis. Here, the given basis is just a standard. It's a standard basis system. It turns out to be the same as this alone. You can do this for the other. I think there's a page missing. This one doesn't seem to be related to anything. Page 13. So was the previous one 12? Yeah, page 12, I think, was not scanned. I have no idea where it is. was just generalizing the FG module. Remind me to go through this next time. There's a page missing. I don't remember it offhand. So the next one is just a definition. This one says a trivial FG module is simply the one-dimensional vector space V over the field F, where every vector V is sent to itself. So it's more like the identity map. And it doesn't matter which element G you pick from the group, this will be true. So this becomes a trivial FG module, the one-dimensional vector space V over F. The one-dimensional vector space over F is just F itself. So the other thing talks definition is a faithful module. FG module is faithful if the identity element is the only element that satisfies this property. So if you check the D8 module, the FD8 module we just studied in the previous example, the only element that satisfies this is the identity element. This is easy to check because there are only 8 elements in the group to check. The only element that sends every vector to itself is the identity element. It is identity element. This one is easy to check. So the example we looked at earlier, this FD8 is a faithful module. So I think the next thing we need to look at are the FG homomorphisms. Would be the next board. So here it is. So there's a section we skipped, the page 12. You can check with your textbook. You will see what has been skipped. But if there's anything that doesn't make sense, if there's anything there that doesn't make sense, we can discuss in the next class. You remind me. I will write it up. So here we have a following setup. We need 2 FG modules, V and W. So function from V, this FG module V to this second FG module W is said to be an FG homomorphism. First, if this map is linear, it's a linear transformation. And secondly, it preserves a group action. In other words, the image of the action of G on V is the same as the image of the action of G on the image of V. And that should be true for all the elements in your FG module V. So that again, that's why I was asking you to look at linear transformations, because the properties now we are going to work with are from linear transformations. You had the whole of last week, so by now it should be familiar. If G is a finite group and theta is an FG homomorphism, then for any vector V, There must be something missing here. Is it correct? We'll come back to it. We don't need it anyway for now. This what we need is this definition. That's what we need going forward. There's something that doesn't seem to be clear here. We haven't defined a group algebra, so this may not make sense. If I use it, I would have to go back and talk about the group algebra. We'll deal with that later. So here's a proposition. It says the following: if V and W are FG modules, and then we have an FG homomorphism. Remember, it must be a linear map, and then it must preserve the action of a group on the vector space V. Then the claim is that the kernel of this map will also be an FG submodule of V. So the other thing we missed was the FG submodules, talking about the submodules. So I'll give you the work to go and read that, but I will write it up again. So the FG submodules work like this. The simple. So if you have an FG module V, you can get a subspace. Let's call it S. So it has to be a subset of V. So S is a subspace of, and for every vector in the subspace, we have the following situation: that VG cannot get outside of S. If this happens, then it becomes a submodule. Not all subspaces will be submodules. Some subspaces will violate this condition, right? So this again induces another endomorphism from S to itself as a subspace where V is sent to VG. So if you have a subspace that still preserves this multiplication, then this should be called a submodule. So we're going to use that in this next theorem. So this one says that theta is a FG homomorphism. Then the kernel must also be a submodule of V. The same should be true of the image. The map, it will be a submodule. These are things I wrote earlier of the previous class. So I'm just cleaning up the screen, then we can. So this simply claims the kernel and the image of this FG homomorphism will be submodules of V and W respectively. So let's check the first one. The first one should be straightforward. This is clear from linear algebra. The kernel of a linear map must be a subspace of V. So you only need to confirm that it preserves the multiplication. Since it's an FG module, it must have some application defined of this form where which still gives you an element in V. So we also know the image, again from linear algebra, the image of theta will be a subspace of W. Directly from the fact that the map is a linear transformation. So suppose we pick an element from the kernel and an element from the group. Yes?
Really is requesting to be admitted.
For it. We're saying if V is in the kernel and G is an element of the group, then you can check if this will be preserved, if this multiplication will be preserved. Since it's an FG homomorphism, this will be true. Theta V will be the same as theta V acting on G, which will be the same as 0 acting on G, and that's just still a 0 vector, right? So this is a 0 because the image in kernel must always be 0. 0G gives you 0. That means that this linear map has sent this element VG to 0, and therefore VG must be in the kernel. So this tells you that the kernel is an FG submodule. It has satisfied the requirements. It's a subspace, and it preserves this multiplication. So we have confirmed that if V is in the kernel, then VG will also be in the kernel. So now it's only a map of theta. So we conclude it's an FG submodule of V, not kernel theta. So this FG submodule of V. So the next thing, again, the image, we know it's a subspace. We just need to check that it preserves the multiplication. So if an element W is in the image, then it means it must be the image of some element V in the vector space V. So we can write W as theta V. Otherwise, it won't be in the image. It must be some. It won't be the image. It must be corresponding to some element V in the vector space V under this map. So this is straight from the definition. Nothing much there. So this multiplication WG is the same as theta V. Left out these brackets because W is the same as the image of V under this map theta. You can place W with this. And since W is an FG module, just hold on. This in the image of theta. I think it's clear. This is already defined. To make this complete, you need to maybe add before writing checking that, confirming that it's in the image, what makes you do that is the following. This being an FG homomorphism, it means you can bring this into the bracket. And now VG is an element of V, and theta acting on an element of V has no choice. It must be in the image of the map theta. That's the missing link. So that tells you that WG, if you pick any element W from the image, then WG will give you an element in the image. So that's the only thing left, because we already established it's a subspace. We now confirm that this multiplication is preserved by the subspace, or rather the subspace is invariant under this multiplication. And therefore we can conclude that it's an FG submodule. So again, just to make it clear, for a submodule, you need two properties. It must be a subspace. That alone is not sufficient. In addition to being a subspace, it must satisfy, it must preserve the multiplication from the FG module. Is that okay?
Yes.
Here are some examples. Of FG homomorphisms. Is the trivial one where every vector in V is sent to the zero vector in W. And the kernel, since all the vectors are sent to zero, then the whole of the domain V will be the kernel. So the next one simply fixes a constant lambda, picks every vector V and sends it to a multiple of V. So this is definitely a linear map. You can prove that this is a linear transformation as long as lambda is fixed. Every vector is sent to a fixed multiple of itself. So we can do that as an exercise, prove that this is a linear map as defined here. I think someone has been knocked out again. Let's bring them back in. So the only element that is such that it's multiple, some non-zero multiple of it is equal to 0. The only way this can work is if V is 0, right? There's no other way it can work. You can prove that in your own time. And therefore, the only element in the kernel will be 0. There's no other vector other than 0 that will satisfy this as long as lambda is non-zero. So maybe we should qualify this by saying that lambda is a non-zero scalar. The next one is a little more interesting. It's called a permutation model. Now, this one requires you to remember some of the work you did in group theory. In particular, you need to remember what we did with the symmetric groups and permutations. Let's follow it carefully. So if we pick a subgroup of Sn, subgroup of Sn is called a permutation group. And we take a finite dimensional vector space with n dimensions so that it is spanned by n vectors. So we will assume that this is the basis. So these vectors are linearly independent. So this will be a permutation module if I think this is on that page 12 that was not scanned. This one assumes you already know the permutation module. The definition of permutation module, but we can still run through this. So suppose just think of it as an FG module and define a map from V to itself as this map that picks because any vector in V can be written as a linear combination of these elements. So this is literally any vector in V you pick, and this will be the expansion in terms of the spanning set, right? So this vector is sent to the following. W is fixed, right? All you do is get the sum of all these values, lambda i's. Now this becomes one number, and then you multiply that by W. So for instance, if these were only two vectors, suppose I'm getting theta of lambda 1 v1 plus lambda 2 v2. So the image of this would be, now I add up the lambdas, lambda 1 plus lambda 2, and then I multiply it by the fixed element, W. Remember, W is the basis for this vector space. So W is a one-dimensional vector space. It is spanned by one vector, W. And the linear map is, the map we are defining is from this vector space that is n-dimensional to this vector space, W, that is one-dimensional. So we need to check that this is an FG homomorphism. So it's a linear map. You can check that it is. It is actually a linear map. So again, I will leave that work as an exercise check that this is a linear map. So you should be able to prove this. Check that it is linear. So let's check if theta acts on a vector V, then you let G act on that vector. This image, theta V, is the same as this thing, right? That's theta V acting on G. But now, this is a one-dimensional vector. It means that WG, one-dimensional vector space, must be equal to W. It can't be anything else. W is the basis. So the basis must be mapped to the basis. Or you can choose it that way. So that forces this WG to be equal to W because it's one dimensional. So it doesn't have any other basis to map to. So if you want to get a kernel, you need to find all vectors in V which are mapped onto 0. So how do you get 0 on this side? The only way you'll get 0 on this side, since W is not 0, is if this sum is 0. The sum of these scalars is 0. So to get those vectors which are mapped onto 0, you need to get all those linear combinations such that the sum of the scale of the coefficients is 0. So for instance, if there are two, you need to get linear combinations that look like this, something like 2v1. Now the sum of these two, such a linear combination will be sent to the 0 element of W, because the sum of the scalars are 0. If there are 3, then you need to find 3 numbers that add up to 0. That linear combination will give you a vector that is in the kernel. So if you get all such linear combinations, you obtain the kernel. The map is surjective. The image is the whole of W. It's a surjective map. I think that's obvious to see. Because the map is made up of elements that are multiples of W. If lambda is some number, you can always get n different numbers which add up to lambda. And those n different numbers will give you an element from V that is mapped onto this element in W. Is that clear? So there's some detail you can add more. I've talked about it, but it's not written on the board. You can add it in your own time. So can we take a 10-minute break? Mtachoka?
Okay.
Muko gangari?
Yes.
So we continue. The next thing we look at are isomorphic FG modules. So there are two things. You need to go and look at these permutation modules. Although it doesn't, it's not very necessary for that part. There's a small topic on permutation modules. This one requires you to understand your group SN, the symmetric group, because you basically will be working with subgroups of SN. Or depending on if SN is small, you may work with the whole of SN, but most of the time it will be subgroups of SN. So here we define an FG homomorphism earlier. So now you just need to add one more thing that makes it an isomorphism. And that is, it's a linear map that is bijective. It's 1, 1, and onto. So it is equivalent to saying that the map is invertible. So if the map is invertible, then the two FG modules are said to be isomorphic. It's simply another FG homomorphism, but we add one more property that it's invertible to make it isomorphism. Since it's just a linear map, invertible means the same thing, will mean the same thing as isomorphism. So this one checks that if you have an isomorphism, FG isomorphism, then the inverse will also be an FG, not just an isomorphism, but an FG isomorphism. So theta inverse is invertible. I think that is follows from the definition. With theta inverse is invertible because if you do this, theta inverse acting on any vector, the theta inverse will give you the identity. So this will end up giving you the same vector V. Maybe you should use W so that it works in reverse order. If you have theta inverse acting first, then theta inverse and theta will usually give you the composition will give you the identity. And this will still give you V. So this one will be a map from V to itself. And this other one will be a map from W, the identity map from W to itself. So all that is happening here is to prove that it is an FG homomorphism. It is definitely a linear map. You should be able to check that theta inverse is a linear map. The only thing that's left here is to check that it preserves this so now the I think I leave this as an exercise. You check carefully. I think it's not too hard. If you go run through this, you should be able to follow that this multiplication is theta inverse acting on W. And then you have G acting on this element should be the same as theta inverse acting on WG. So you have what you will use is the fact that the map is an isomorphism. Let's just check that there's no error in the statements. I think this one probably won't make sense. Maybe necessary to leave it out. So you need to have theta acting on theta inverse WG. Since theta is an FG homomorphism, it's possible to pull out this vector, right? This is a vector in V, remember, from the definition. So it's possible to isolate it here as a vector from G using the fact that theta is an FG homomorphism. Just from the definition, this will be true. So then the G is outside. But now theta inverse will give you the identity, right? So the identity will just give you W. The identity acting on W will give you W. This is using the notation, like I told you, the book writes the argument If it, instead of theta W, it write W theta. It puts the argument on the left. So here I've used the notation that you can ignore this first line. This one was using the notation in the book, so it needed to be crossed. So the one we are using is this. And using the fact that theta is an FG homomorphism, you can isolate this as a vector in V, because theta inverse sends elements from W back to V. And since theta is invertible, theta and theta inverse will give you the identity. So it leaves you with just W here, WG. But now WG is the same thing. What is going on at the bottom here is the same thing as the identity element acting on WG. Remember, WG is an element in W, but you can replace the identity element to just theta and theta inverse, which eventually you can write as theta inverse WG. Using the fact that now theta, because we have theta here and theta here again, using the fact that theta is an isomorphism, it means it is 1-to-1, as well as being onto, but the property we need here is 1-to-1. So the only way this can be true is if this item in the bracket is equal to this one in the bracket. Yeah. So basically, we can make that claim using the fact that theta is an isomorphism, which means it's injective. If it's injective, the only way this can be true is if this is equal to that, and that is what we state here. So this item is stated here, theta inverse, this theta here, inverse W bracket, and then G, that's this term here, has no choice but to be equal to this term here. But now this is what proves that theta inverse is an FG homomorphism. This is W. That proves that theta is an FG homomorphism. I mean, not theta inverse. Theta itself was already stated to be an FG homomorphism. So we are told it's invertible. So the only thing we needed to show is that the inverse is also an FG homomorphism. The only thing we have not shown here is that the inverse is a linear map. So make sure you check that. Those are the two things you need to prove. It's a linear map and it preserves this multiplication. Are we clear? I wanted to leave it as an exercise, but I've ended up going through it. So I've saved you the trouble. But not all is lost. We still have a chance to shine here. There's an exercise here for you. So take this. There's some statement here which says that if theta is an FG isomorphism, keyword is isomorphism, then the two vectors, the two FG modules must be of the same dimension. Assuming they're finite, also we are working with finite dimensional vector spaces, so the dimension of V is the same as the dimension of W. As long as it's an isomorphism. Again, this is easy to check from your linear algebra, the chapter I told you to read, that will answer this problem for you. You'll have to set up a basis for V, find the images of the basis element, and use the fact that it's an isomorphism to show that the images of the basis elements of V also span W and are linearly independent, and therefore they have the same, the dimension of V and W will be the same. So now this talks about irreducible. Again, there's, like I said, there's a section on submodules that we left out. So we say that an FG module is irreducible if the only submodules are the zero submodule or the subspace containing only the zero element and the whole So if it's irreducible, these are the only submodules. There are no other submodules. That makes it irreducible. So use that fact. If V is irreducible, then W must also be irreducible. Following from the fact that the map theta is an isomorphism. This is key. Throughout, you have to make use of this property. That the map is an isomorphism. And then the third one says V contains a trivial FG submodule if W contains a trivial FG submodule. So I'll leave this as an exercise. These three should be enough to keep you busy. So there's a statement here that says if you have two isomorphic modules, it's possible to show that they correspond to equivalent representations. Remember, we say that two representations are equivalent if what happens, if we can get, so that if rho G be written as some invertible matrix, I think this was supposed to be just hold on. We said rho is equivalent to sigma if the following happens. Rho is equivalent to sigma if sigma can be written as the image of G under sigma should be the same as some invertible matrix T inverse multiplied by the image of G under rho, and then so this is what we saw in the earlier lectures, the equivalence of two presentations. So again, earlier on we saw that if you have an FG module, the FG module will also induce some linear map. The linear map that is induced by the FG module is this one, where V is sent to VG under the multiplication defined in that FG module. So this one we established. This one becomes a linear map. So the claim is that it's possible if you have W to WG, and then you set up, V to VG, then you set up another map in the other FG module. Then these representations which are induced through this map where G is sent to its. So this might be some basis, we call B1, and the other one is what? Again, this one will give you another representation, which sends, let's call this basis B2, this being a basis of W, and this one being a basis of V. So the claim is that these representations can be shown to be equivalent. So again, that is stated in the following theorem. It says, suppose that V is an FG module with basis B and W is an FG module, basis beta prime. So I need this one, I call them B1 and B2. Then V and W are isomorphic if these representations, if and only if, you see it's a double F, so it's a, you have to prove the theorem and it's converse. So essentially it says if these V and W are isomorphic, then these two representations are equivalent. And also if you can show that these two representations are equivalent, these two representations of a group G, if they are equivalent, then it forces V and W be isomorphic. physicists suppose that theta is an FG isomorphism from V to W, and we set up a basis for V. So you can now show that this theta V1 up to Vn is as a basis of W. Remember, this is what I was telling you to use. Set up a basis. The images, since it's an isomorphism, the images of the elements, basis elements of V, we form a basis for W. So to get a basis for W, you just need to find the images of all these basis vectors for V. So now you have a basis for W, you also have a basis for V. Now, there's a big story here that is being skipped. I don't know whether I should let you find it or I should cover the story. Good. There's a bit of work to be done here. It's been stated rather casually here that these two matrices must be equal. So this first matrix B1 is the one which is determined by this map. V is the one sent to VG. The matrix for this map. This probably will get you started. So this first one is a matrix for this map with respect to the basis beta 1 in V. So this takes care of the endomorphism, or rather the representation that is induced by this FG module. Under this map, you'll be able to set up, because you're working in V now, your basis must be from V. So this gives you B1, right? And the representation you are looking for is this one. So then there's another map now, again, which takes W to WG, but W of course can be written as any vector in W, since it's an onto map. Any vector in W can be written as an image of some element in G. So if I have W, this is the same as theta of V for some element in V. Is that correct? No, not phi, theta. So if I have G going to WG, now at this point, not G, V. W is going to WG. Then let me delete this. So this new map now in W, this is the endomorphism induced by W as an FG module. I will need a matrix for this as well. That matrix will be, since now I'm in W, the vector space W, I will need the basis for that vector space, which is B2. Then this map that sends G to this matrix, G with respect to basis 2, is supposed to be a representation. So these two representations are supposed to be equivalent. So that means I should be able to, these two matrices, they should be similar. Similar in the sense that similar means if I take this as a matrix A, I should be able to write it as T inverse. If I take this one as B, T inverse BT. The change of basis. So I think you can use that to try to complete the proof. So then there's a converse as well, which assumes that you have two equivalent representations. There's some breaking down to be done here. I will let you do that. If you get stuck, we can go over this. So there's a theorem itself that assumes that we have these two isomorphic FG modules. And it shows that these representations are equivalent. And the converse as well. So I'll leave that as your small homework. You can also look at the one in the textbook to compare. So there's an example that illustrates that here. You have the cyclic group of order 3. It can be set up as follows. You also set up a cyclic group of order 3 from the general linear group of 3 by 3 matrices. So the permutations in S3 can all be represented by 3 by 3 matrices as follows. These are called the elementary matrices. These elementary matrices can be used to represent they behave like the elements in S3. You can replace all of them, but these ones just picks 3 of the elements in S3. The rotations, if you want, they happen to coincide with B3, so you can think of them as the rotations. I don't know if that makes sense. What I'm saying is if you, I'll give an example. If you have this element, this element from S3, 1, 2, 3. So this is a cyclic notation, if you recall. This means 1 is sent to 2, 2 is sent to 3, and 3 is sent to 1. You can do that same operation on the identity matrix. So the first row is sent to the second. So the first row is 1, 0, 0. The first row of the identity matrix is sent there. The second row of the identity matrix is this. It is sent to the third. So the second row is sent to the third. Second row looks like this. And the third is supposed to be sent to 1. So this element corresponds to this permutation matrix. You can try the others that are not for instance, if you consider the other element 1, 2, 1, 2 leaves the third row fixed and switches the first and the second. So the third row does not move. The first and the second will switch. So the first goes to where the second was, the second goes to where the first was. So you can represent each of these using this. They behave the same way. Is that making sense?
Yes.
Good. So that's how you connect them. So this example now should make sense. If you sit down to read it carefully and connect it to the previous theorem, then this will make sense now. And this one, I think, is talking about the group algebra. I'll leave this out until we cover something of that nature. Again, then this is an example of the same. Let you read that example. It makes uses of now this one is interesting because it uses the general linear group now is not for real numbers. It's also the field is complex numbers because you have some complex numbers in here. Sorry, you start with the degree, which is n. So here, the general linear group is over the complex numbers for this example. So you pay attention to that as you go through this example. You have to sit down and go through this very carefully. It's quite detailed. It requires your full attention. You have to find a nice quiet place where you can sit down and go through this line by line. And you must understand every single line, what's happening. If you have questions, you can ask them in the next class. Let me connect my battery. It's going down and forgotten to connect power. So I don't know. Start topic now. Just one last bit, then we can, as you had suggested last time, we can try to meet again later. I think I'm also tired of talking. I've been talking for 1.5 hours now. We can talk about direct sums. That's the last thing for this. So you must have, I told you to check the linear algebra bit. So that chapter also talks about direct sums of subspaces of a vector space. In this case, we're interested in subspaces that are also FG modules, and therefore we can call them submodules. So if you have an FG module, and suppose it's possible to write V as a direct sum of two FG submodules, U and W. suppose U1 to UM is a basis for this subspace. So direct sum simply means that if you have actually looked through the work, it means the intersection of U and W is just the zero vector. Other than that, they don't have anything else in common. And any element in V can be written uniquely as some element U from the space U plus another element W from the space W. This sum is unique. That's what makes it a direct sum. So you can only find one U and one W for this vector V. If you pick another vector, you will get a different combination of U and W, not the same combination. So that's what it means for a direct sum. So if you take U as a subspace on its own, it will have a basis. Take W as a subspace on its own, it will have a basis as well. So for U, we have U1 up to UM, M for Mandizi, and then W1 to Wn, where N is for Nairobi. So these two bases, if you combine them together, they will form a basis for V, right? If you combine these two together, they will form a basis for V. And using such a basis that comes from the direct sum, then your matrix G with respect to that basis will be of this form, right? It will be a block matrix of this form, where you have one matrix here, another matrix here. Now this matrix here is obtained by using U as an FG module, right? And if you use U as an FG module, then it's possible eventually you can have some map that sends elements of G to this matrix with respect to the basis from U1. So if you just work with U itself as an FG module, you can do that. If you work with the other subspace W itself, again, you can set up this map, which also gives you this as your matrix, but now with a basis for W. Now these two can be plugged in here together to get now, instead of dealing with U and W separately, you can deal with now the whole space V. The whole space V will also give you another call it matrix representation with respect to the basis B. The basis B is a union of B1 and B2. Now this new matrix is the one that will look like this. So how does this work? Let me move this. Oh, I still have the old computation from the last class here. We can start afresh. So this is a situation we have. V is equal to the direct sum of U and W. So if I pick an element from V, it's possible for me to write it as a linear combination of, let's call it alpha 1 U1 plus alpha 2 U2. This keeps going on like that, plus alpha There are only M of them for you. And then you can see what I'm writing. Hello? Yeah. Can you hear me?
Yes, we can.
Yes.
You also see what I'm writing? Or
Yeah.
okay. There's a reason I'm asking, because sometimes when I shift the board, people don't see. So it's important to know that you can see. So the basis is extended using the elements, basis elements for W. So you can now start from W1 here. Might be a better way of writing this, but for now, let's work with this arrangement. So now the last one here is beta N W N. So that means the dimension of V should be M plus N. This is a number of basis vectors in a basis for V. So any vector V can be written like this. So if you want the matrix for this linear transformation, the linear transformation that goes this linear transformation that goes like this, V to Vg. Now, since Vg is just in V, so you'll need to get the image of each basis vector. So V1 will be sent to V1G. But now V1 can be written as not V1, it's actually U1. It's U1G, right? The basis elements are V1 up to UM and then W1 up to WN. So you have to start with the first one until you exhaust all of them. So the image of U1 is the same as U1G under this linear map. So the idea is to get the matrix, you need to get the linear, what do you call it? The linear combinations of the basis vectors. Also take advantage, the other thing is that U is a submodule. So this U1 comes from U. So U1G will also be an element in U, right? So keep that. So U1G acting on U1 will be an element still in U. Since it's wholly in U and the basis for U consists of just these vectors U1 up to UM, you don't need any vectors from W to write out U1 or the image of U1. So this image can be written as a linear combination. Let's now say alpha 1 1 U1. So this will run all the way up to alpha 1M U M. Now this basis vector came from U, and U is a subspace with its own basis. So those basis elements are enough to write out U. So I can only introduce the others with zero, the ones from W with zero coefficients because they don't contribute anything. So this will go all the way up to 0, Wn. Do the same for the next one. If you have V2, V2 will be sent to V2G. Not V, it's now U. U2 will be sent to U2. We are picking the elements in the basis, U1 all the way up to Wn. For U2, let's make it clear. We have U2 acting on G. But now this, because U is so the same thing will happen. U2 came from U. So U2G cannot be outside U because U is a submodule. So that means even this one can now be written as alpha 21 U1 plus alpha 2M UM. Again, all the other coefficients will be 0. These will all be 0 up to Wn. So for now, you get the picture. This will go on until you get to UM, which was the last one here. Again, you will have coefficients for the U's only, because to express anything from U, you only need the basis vectors in U. Then UM. The others will be 0. Again, you can use them out properly. Go up to 0 Wn. 0 W1, keep adding until you get to Wn. So that takes care of the first set of basis vectors. The next set of basis vectors now starts from W. Now these ones, W1 normally is supposed to be sent under that linear map is sent to W1G. But remember, W1 again is from our vector space W, and W is an FG submodule, so W1G cannot go outside W, which means this is a vector in W, fully in W, and therefore you only need the basis elements from W to write the linear combination, which forces all these others from U to be with 0 coefficient, UM. Then you will start the one from, we can call it beta 1 plus multiplied by W1. And this keeps going on until you get to beta 1N multiplied by Wn. So this continues like this until you get to the last one, Wm. Wm is sent to Wg. Again, Wmg is an element in W. So you don't need any vectors in U. So all the vectors in U will have 0 coefficients. And here you'll have what? Beta. The last one was Wn, not M. I think it's N. So you beta N1, W1 up to be beta NN now. Wn. So remember, the matrix of a linear transformation is simply the coefficients. You pick the coefficients from here. So you'll have 2 blocks. There's this block, which gives you the coefficients. I'll skip writing them. I'll just write them as a block. So now this also turns out to be the same as the matrix of, if you restrict yourself to the basis for U, which we call it B1, let's just call it B1. Here it's 0 because you can see all these are all zeros. So the same will happen here, 0, because all these have 0 coefficients. Then you will have your other matrix here, G, but now with the basis for W. The same thing. So it makes use of the properties of direct products and then linear maps as well. Is that okay? Any questions on this? This one requires your full attention. You really must sit down and burn the midnight oil. There's no shortcut for this one. It's not a very straightforward thing. For you to master it, you have to give it your attention. So are we? Did it make sense?
Yes.
Is that a yes or didn't come out clearly?
Yes, it makes sense.
So I think we can stop there for today. We'll pick this up in the next class. Then let's see how the week goes. Maybe we can have one more class somewhere in the course of the week. We agreed it's better when we have another class in about 1 hour, so I can't continue with this one now. I'm also tired of talking. I have a mouth ulcer here, which is giving me trouble, so I need to rest it a bit.
Okay.
We'll communicate and see when it's possible to have another class this week.
I will organize and tell you.
Okay. Did I share the recording for the last class?
No.
Okay. And you did not remind me. It means you are, maybe you understood the previous well.
Request Mariah to request it from you.
You want to impeach Mora?
Para tusikize Mrima.
Hataki kuza Mrima.
Mrima tuweze kuza Mrima.
He knows very well. He's not even, he knows you cannot touch the Mrima.
Yeah.